All right, you are welcome to this week's class. So, this week we'll talk about electric field, electric flux, Gauss law. So, these are the subtopics: the electric field, electric flux, Gauss law, electric potential, potential difference. So, we'll start with electric field. What is an electric field? An electric field is a region of space in which a charge will experience an electric force. Okay, so it's a region. So let's say this is the region. So within this region, any charge that is within this region will experience an electric force. But outside the region, the charge will not experience any electric force. So that is an electric field. Now, so if let's say a charge Q, okay, so let's denote our charge by Q. And this charge is acted by a force F, which is a vector. So the electric field E, it's also a vector, at that point is defined as the ratio of the force per the unit charge. So the electric field equals the force per unit charge. So let me write this separately. So the electric field equals force per unit charge. Okay, so if you know the force, then you can easily determine the electric field. Now, this electric field is a vector quantity. So electric field E is a vector quantity. It's a vector quantity. And the unit can be Newton per coulomb. In this case, you have the force is Newton, the charge is coulomb. Another unit is volts per meter. We'll get to that shortly. Volts per meter can also be the unit of electric field. Now, in equation 1, from equation 1, if you cross multiply, we can have F, the force, equals QE. So it means if we know the electric field, we can easily determine the force that is acting on the charge E. Now, from Coulomb's law, so the force is a constant, the two charges, so let's say QQ prime over R square, where R is the distance. So let's say this is Q and this is Q prime. So R is the distance between the two charges. So the force of either attraction or repulsion between these two charges, is F equals KQ Q prime over R squared. Now, if we know this, it means if we use this in equation 1, okay, using this in equation 1, equation 1 is E equals force per unit charge. So it means instead of putting F, we put KQ Q prime over R squared divided by 1Q. Okay? So it means this can be written as KQ over R squared, or KQ prime over R squared. Okay? So this can be a relationship between the electric field and the charge that is in that field. So this K is a constant. So this K is 1 over 4 pi epsilon naught, where epsilon naught is the permittivity of free space. So this value is approximately 9.0 times 10 to the power 9. That will be Newton meter squared per coulomb squared. Okay, so that is the constant. So next, 2.0. Electric flux. Now, the electric flux, I'm going to use phi, capital letter phi, as my electric flux. So it can be defined. All right. So the electric flux is defined to be a measure of the amount of electric field that crosses a certain area perpendicularly. So if we denote the electric flux by the phi, so and it crosses a small area element dA, then the flux is given by the scalar product of the electric field and the area vector. Okay, so this is shown in equation 2. So the phi is the flux that crosses a small area element dA. Now, if the angle between the electric field vector and the area vector is theta, then we can write the phi, the electric flux, as E A, that's modulus of E, the modulus of A cos theta, where theta is the angle between the electric field vector and the area vector. Now, the unit of measurement of electric flux. So, SI unit of electric flux can be Newton meter squared per coulomb squared. So you can write it like this, or you can write it as this. So this is the unit. Okay, this is the unit of the electric flux, and it is a scalar quantity. Okay, it is a scalar quantity. It's a scalar quantity. So, but electric field is a vector quantity. Electric field is a vector quantity. Now, this electric flux, if we move from equation 3 or even from equation 2, we want to find the total flux. Okay, let's use equation 2. From equation 2, okay, the total flux, this is just an elemental, this d phi here is for the area element dA. So if we want to find the total flux through a closed surface, let's say the surface is S. So that flux can be written as capital letter phi equals the integral, so which is over a closed surface. So this circle around this integral means that the integral is over a closed surface. So that is the essence of the circle. So it's going to be, if you check equation 2, the phi equals E dot dA. So if you take the integral, so it will be phi equals the integral of the scalar product of E and the area vector A. So this is what you have. And of course, we can also write this as the integral of E A cos theta, or E cos theta, then with respect to A. So let me call this equation 4. So this is equation 4. Okay, so it means from this equation 4, we can reduce it further if we know that the electric flux is constant. Okay, so we can say that the electric flux phi, capital letter phi, equals EA cos theta. Okay, EA cos theta, or we can write it as the scalar product of E dot A. Okay, anyone. So in this case, we assume that the E is a constant. Okay, it's a constant. So it means we can bring the E outside the integral. Then we have, so from this equation 4, we have capital letter phi equals the closed integral of E dot A. Then if E is a constant, then we can bring E outside, then the integral of the A. Okay, so and this can be E dot the vector A. So phi can be E dot A or EA cos theta. Why? Because the scalar product of two vectors is the modulus of the first, modulus of the second, cos theta. Okay, so in this case, this E means the modulus of the vector E, and this A means the modulus of the area vector. Now, as I stated here, I said the electric flux is a scalar quantity. So the electric flux can have the electric flux can be positive, it can be positive, it can have a positive value, it can have a negative value, it can be zero. Okay, so it can be zero. It can have a positive value, it can have a negative value, and it can be zero. Now, another thing that you should note is this. If the electric flux line, okay, if it goes, or the lines, let's say the lines go into a closed surface, okay, let me explain with the diagram. So let's say we have this surface, this is the surface, and the electric field vector goes, the line, let's just take one line, there are many lines actually, but let's just use a line. So if the line goes into the closed surface, then the flux is going to be negative, and we'll see that shortly. We'll see the reason why it is negative. So in this case, so this is the electric vector E. It goes into this surface. So let's call the surface S. Then in that case, the flux is going to be what? Negative. Okay, but if let's say we have, this is the surface S, and the electric field goes outward, okay, from the closed surface S. So this is the electric field vector. Then in that case, the electric flux is going to be what? It's going to be positive. Okay, we will see from the examples that I will give shortly the reason why the flux, it will be negative or positive. Okay, let me start with this example. So example 1. All right, so let's take a look at this example. A flat surface of area 3.2 meters squared. So the area of the surface is 3.2 meters squared. Is rotated in a uniform electric field of magnitude E equals 6.2 times 10 to the power 2 Newton per coulomb. So this is a constant electric field. Electric field here is constant. So the question is, determine the electric flux through this area when the electric field is. So there are 4 cases that are given, and I've given these 4 cases so that I will explain all the various situations that you can come across. So the first one is that when the electric field is perpendicular to the surface. The second, when the electric field is parallel to the surface. The third, when the electric field is perpendicular to the area vector. And the fourth one is when the electric field is parallel to the area vector. Now, so let me say the first part. Now, so let's say this is a surface. Okay, this is a surface, and the question says we are given let me write E is 6.2 times 10 to the power 2 newtons per coulomb, and the area is 3.2 meters squared. Now, how do we determine the flux? The flux can be determined here using E A cos theta. Since the electric field here is constant, okay, the area is also constant. So the only thing that is changing here is the angle between the electric field and the area vector. Now, if you have a surface, let's say the surface is sitting horizontally, is resting on a horizontal surface. It is not standing vertically. It is not standing perpendicular to the horizontal surface. It is resting on a horizontal surface. Now, the normal to this will now be perpendicular to the horizontal surface, which is the area. So this is the area vector. Now, the question says the electric field is perpendicular to the surface. So this is the area vector. Let me use another color to denote the electric field. So the electric field is also perpendicular to the surface. So this is the electric field. So the surface is sitting horizontally. Okay. So the area vector is perpendicular always. The area vector is always perpendicular to the surface. This is constant. This is always the case. But the electric field, the direction of the electric field can change. In this case, the question says that the the electric field is perpendicular to the surface. So it's the angle between the electric field and the horizontal. We are taking the surface to be resting horizontally. Is here. Now, if you look at these two cases, the area vector is pointing upward, the electric field vector is also pointing upward. So it means the angle between the two is what? Is 0 degrees. So it means if you want to determine the electric flux, so we can now say that the electric flux equals the electric field, which is 6.20 times 10⁻²newtons per coulomb, multiplied by the area 3.20 meters squared, then cos 0 degrees. The angle between them here is 0 degrees. Okay, so if you take your calculator and do this simple arithmetic, so you have 6.2 times 10⁻², okay, that is 620 multiplied by 3.2 multiplied by cos 0. Cos 0 is 1. Okay, so let's just say cos 0. So we have 1984. 1984. So this is 1984, and the unit will be Newton meter squared per coulomb. So this is the first case. Now, the second case, we are told that the electric field is what? Is parallel to the surface. So again, let's say this is the surface. Okay. So again, the area vector is always perpendicular to the surface. So this is the area vector. Now, but in this case, we are told that the electric field is now parallel to the surface. So the electric field is now parallel to the surface. So this is the electric field. It's now parallel to the surface. Okay. So in this case, the angle between the electric field and the area is what? Is 90 degrees. So if that is the case, it means the electric flux, phi, which equals EA cos theta, so will be equal to the electric flux, the electric field is 6.2 times 10⁻² newtons per coulomb, multiplied by the area, which is 3.2 meters squared. Now multiplied by cos 90 degrees. Cos 90 degrees. Now if you check cos 90 degrees, so it is 0. So it means everything here is going to be what? 0. So the flux here is what? 0. Now, what about the third case? The third case, we are told that the electric flux is perpendicular to the area vector. So it's already perpendicular to the area vector. So in fact, we do not even need to sketch anything, but let me still sketch it so that you understand what I'm saying. So in this case, let's say the area vector is in this direction. The electric field, they said, is perpendicular to the area vector. So it means the electric field is going to be like this, perpendicular. So that the angle, so this is the electric field direction, the angle theta is going to be what? 90 degrees. And in that case, the electric flux will also be 0. Okay, so this is the area vector A. It is perpendicular to the, so the area vector A is perpendicular to the electric field. Okay, so what you need to do here is, if you are given the angle between the electric field and the area vector straight, so all you need to do is just put phi equals EA cos 90 degrees. Okay, so if you are told that the angle between the electric field and the area is 30 degrees, just do EA multiplied by cos 30 degrees. But if you are told that the angle is at a certain angle to the surface, okay, so then it means you have to determine the original angle. Okay, so but in this case, you are told that the angle is between the electric field and the area vector, not to the surface. Okay, now the last one is that the electric field is parallel to the area vector. So parallel, so phi is EA cos theta. if they are parallel, if E is parallel to A, so it means the angle between them is what? Is 0. And cos 0 is what? Is 1. So it means this case will be the first case that we did, which is 1984 Newton meter squared per coulomb. Okay, let me give another example. Alright, so this is the question. So calculate the electric flux crossing a square region outside 4 meters where the electric field is directed perpendicularly into the plane of the region. The magnitude of the electric field crossing the area is 100 newtons per coulomb. So solution. So the electric field is 100 newtons per coulomb. The area, to determine the area, we're given the length of is a square. So the area is L squared, okay, which is 4 meter squared, which is 16 meter squared. So that is the area. So our job is to calculate here also the electric flux. So how do you determine the electric flux in this case? Now again, is a square. So let's say this is the surface. This is the surface, and we are told that the calculate the crossing. So we are told that the electric field is directed perpendicularly into the plane. So the electric flux is directed into the plane, perpendicular into the plane. So this is the electric flux. Okay. Now, what about the area? Again, as I explained earlier, the area is always out the plane, perpendicularly outside the plane. So this is the area. If you look at these two cases, what is the angle between the electric field vector and the area vector? Can you guess? What will be the angle between the electric field vector and the area vector? It is not 0. If they were to be moving in the same direction, then the angle will be 0. Okay? If one is like this, if one is like in this case and the other is like this, so here the angle is 90 degrees, but in this case one is going up, the other is coming downward, so the angle here is 180 degrees. Okay, so in that case the electric flux is going to be EA cos theta. So that we have the electric field is 100 newtons per coulomb, the area is 16 meters squared, and the angle is 180 degrees. So that the electric flux will be 100 multiplied by 16 multiplied by cos 180. So we have minus 1,600 Newton meter square per coulomb. You know, I said this earlier that the electric flux can be positive, negative, or 0. So here it is negative. Why? Because the electric field is directed into the surface. It's directed into the surface. So here in this case, it is what? It is 0. So next is Gauss law. So let me check the numbering. So that will be 3.0. So 3.0 Gauss law. Now, this Gauss law, it says that the total electric flux, we have talked about previously, we said the electric flux is given by the integral of the scalar product of the electric field and the area vector. Now, Gauss law now states that this electric flux, okay, that it is equal to the ratio of the charge to the permittivity of free space, Q over epsilon naught. Okay, so the Gauss law states that. So let me just try to state it. So Gauss law states that the total. Okay, so we can say Gauss law states that the total electric flux crossing a closed surface is proportional to the electric charge enclosed by the surface. So mathematically, so the integral around the closed surface of the scalar product of E with the area vector equals the ratio of the charge to permittivity of free space. So this epsilon naught is the permittivity of free space, and it is 1 over 4 pi k, so which equals approximately 8.85 times 10 per minus 12 coulomb squared per Newton per meter squared. So it is called permittivity of free space. Permittivity of free space or vacuum. Okay, and this is the approximate value. All right, how do we prove this? How do we prove that the electric flux equals Q over epsilon naught? So what we can do, we can say, let's consider the flux, due to, that is the electric flux, okay, due to a positive point charge. So let's take a positive point charge, okay, which is Q, on a spherical surface centered at the charge. Okay, now we'll take the radius. So the radius of the spherical surface to be R. So we denote the radius of the spherical surface by R. So the small area, let's take an elemental area, we denote that as dA, and the electric flux, of course, is what? Is E. The electric field is E. Now, from the definition of flux, which is phi, or the phi equals, phi equals integral E dot dA. Okay, so if you have a situation where the electric field is constant, okay, it means we can take E outside the integral. We can take E outside the integral, then we can do A. So E dot dA. Now, from Coulomb's law, I think we have worked the value of E. So let me check the equation number. The electric field, that is under electric field. Yes, so KQ over R squared. So electric field is KQ over R squared. So E equals KQ over R. So in this case, it is capital letter R. The radius is capital letter R. And the area, since it is a sphere, okay, volume of a sphere is 4 over 3 by R cubed. So area is the derivative of the volume with respect to the radius. So here, if you differentiate this with respect to R, you get 3 times this. So 3 will cancel 3. So you have 4 pi R squared. So the area, the elemental area is 4 pi R squared. So that this flux, or this integral, dA, we can write it as I've already taken the E outside. So let me place E here, then dot the area. Okay, so that we now have the electric field is KQ over R squared, and the area is 4 pi R squared. So, and this will give us 4 pi KQ. Okay, yes, R squared will cancel R squared. Now, K is 1 over 4 pi epsilon naught. So, K is 1 over 4 pi epsilon naught. So, I've defined, so here I defined epsilon naught as 1 over 4 pi K. So, we can also write it as K equals 1 over 4 pi epsilon naught. Okay, so that we replace K with 1 over 4 pi epsilon naught here. So 4 pi will cancel 4 pi. Then we'll be left with Q. So we'll be left with Q over what? Over epsilon naught. So therefore, the integral over the closed surface of E dot dA is what? Is Q over epsilon naught. So this is Gauss law. So this is we have proved Gauss law. All right. So let's take an example. So let's take an example. Okay, so this is a simple example. 3 particles of charges 2 nanocoulomb, minus 6 nanocoulomb, and 9 nanocoulomb are located on the x-axis at the point x equals 1 centimeter. So 2 nanocoulomb is located at 1 centimeter, minus 6 nanocoulomb located at 3 centimeters, and 9 nanocoulomb located at 5 centimeters. Now the question says calculate the electric flux crossing a Gaussian surface of radius 4 centimeters centered at the origin. So the question is very simple. So to calculate the flux, so Gauss law states that it is the total charge divided by epsilon naught, total charge on the surface. Now, if we say, let's just take that this is the surface and the radius, this is the surface where the electric field lies. So the radius is 4 centimeters. Now, if you look at the first charge, it is 2 nanocoulomb, right? It is at 1 centimeter, so it is within, so Q1, so I call the first charge, is within 4 centimeters. So the electric field covers the first charge. The second charge is minus 6 nanocoulomb. So let's say Q1 is 2 nanocoulomb, and the position is at 1 centimeter. Q2 is minus 6 nanocoulomb, and the position R2 is at 3 centimeters. Then Q3 is 9 nanocoulomb, and the position R3 is what? Is 5 centimeters. So Q1, which is position 1 centimeter, lies in this radius. Q2 is 3 centimeters. It also lies in this radius. However, Q3 is 5 centimeters. It lies outside this region, outside the surface, so it is not considered. Okay, so the charge that will be considered will be plus 2 nanocoulomb, then plus minus 6 nanocoulomb. So plus 2 minus 6, that will be minus 4 nanocoulomb, and that will be minus 4 times 10 to the power minus 9 coulomb. Okay, so that the electric flux in this case is now Q over epsilon naught, which is minus 4 times 10 to the power minus 9 coulomb, or the magnitude, so divided by 8.85 times 10 to the power minus 12 coulomb squared per Newton per meter squared. So and this is approximately 451.977. So you can say 98 Newton meter squared per coulomb. So that will be the electric flux. Okay, so the first assignment I'll give you today, assignment 1. So charges. So this is the assignment. Charges plus Q minus 4Q and plus 2Q are placed inside the cube enclosure, but their positions are not specified. What is the total electric flux passing through the walls of the container? So this is your first assignment for today. So next, so I think that will be 3 or 4. Okay, that will be 4.0. So 4.0, electric potential. Okay. Now, electrostatic force is a conservative force. Is an example of a conservative force field. So electrostatic force is a conservative force. So if you have a conservative force, it means we can obtain a potential. Okay, we can obtain a potential. Now, the work done, let's define the work done by a conservative force. So the work done by a conservative force, let's denote the work done as W underscore C, meaning conservative force. In moving or displacing a charge by an infinitely small displacement, so let's denote that as dr. So the electrostatic, the work done by a conservative force, I said we denote that as W underscore subscript C, is defined as to be the negative of the change in the potential energy. Okay, so the work done is minus delta W, where delta W is the change in potential energy. So U is denotes the potential energy. So delta W is the change in potential energy. Now, of course, we know that work done is the scalar product of force and displacement. Okay, so if we consider a small displacement, dr, okay, and the force that acts to displace an object by this dr, we call the electric force F subscript E. So it means the work done, so the W that is done to move an object this small distance, displacement, is the scalar product of the force and the displacement vector. Okay, now this is from the definition of work done. Now, if we now take the total work done, okay, so the work done in, let's say we now displace an object from position Ri, in displacing the charge from the first position, the initial position Ri, which is a vector, to the final position Rf. So we displace an object from Ri to Rf. So the work done is the integral from Ri to Rf. So we take the integral of this equation 7. So that's what we do. We integrate this equation 7. So that it will be F subscript E. We are using Fe as the electric force dot dr. F dot dr. So this is the work done. Equals the integral, the work done in displacing a charge from position Ri to position Rf. So it is given as this. So let me call this equation, this is an important equation 8. Okay, of course we can reduce this equation if we know that or before that, from our definition, if you check probably equation 1 or equation 2, this equation 1 or equation 2. Oh, okay. So either this equation 1 or this equation. Okay. So F is QE. Okay. This equation 1 is from the definition of electric force. Now, and I said if you cross multiply, you have F equals what? QE. So if we now substitute F equals QE into this expression, okay, since F equals QE, it means we can write our work done as what? As instead of Fe, we now write what? QE. Q is a constant, we can take it outside. Ri, the initial, these are vectors. To Ri to Rf, then the electric field dot dr. Okay, so let me label this as equation 9. Now, and of course, if the electric field is a constant, so if E is constant, then we can also take it outside so that we can have electric field equals QE, then dot the integral of Ri to Rf dr, or we can write it as QE dot delta R. So where delta R is this integral. So this delta R is, so we can write WE, which is the work done, equals QE dot delta R, or Q E R cos theta. Why? Because the scalar product of two vectors A and B is the modulus of A, the modulus of B, cos theta. Okay, so in this case, this E is the modulus of the vector E, and this R, so R is the modulus of the vector R, and this theta is the angle between the electric field and the position vector. It's the angle between the electric field, and the displacement. Displacement of the position vector. Okay, so this, I think there are important equations there. This is one of them. I've labeled equation 9. Equation 10 is also important. So if the electric field is a constant, so we can use this equation 10. All right, so of course the unit of work done is joule, so I think that is simple. So let's take an example. All right, so the example is a 2 microcoulomb charge is displaced from the location 2i minus 3j meters to the location minus 4i plus 9j meters in a region where there is a constant electric field. So the electric field is constant, so it means we can use equation 10. Since the electric field is what? Is constant, we can use equation 10. And the value of the electric field is given as minus 10i minus 4j. So the question is calculate the work done by the electric force. So to determine the work done, we can use equation 10, so solution. So we use equation 10, which is the work done equals Q electric vector dot the displacement vector. Okay, now the charge is given as 2 microcoulomb, which is 2 times 10 to the power minus 6 coulomb. The electric field is a vector. It is given as minus 10i minus 4j newtons per coulomb. The displacement vector, the R, is what? Is R2 minus R1. What is R2? R2 is given as minus 4i plus 9j. So minus 4i plus 9j meters. Then minus R1 is 2i minus 3j. 2i minus 3j meters. So if you subtract the two, then the position vector, the displacement vector, is going to be minus 4, this minus 4, minus this 2. Minus 4 minus 2, that's minus 6. Okay, I. Then the j components, 9 minus 3. So that will be 9 plus 3. That will be plus 12j meters. Okay, so I think you have been taught how to find the difference between two vectors. So if you want to find the difference between these two vectors, a minus b, is going to be a, the x component of a minus the x component of b, then plus the y component of a minus y component of b, plus the z component of a minus the z component of b. So if this is plus, then it will be plus here, plus here, plus here, so plus or minus. Okay, so in this case, this is ax, so minus 4, then minus ay, which is 2. Okay, so minus 4 minus 2 is minus 6, then 9 minus minus 3, that will be 9 plus 3, which is 12. So that the work done that we have to calculate is then going to be Q, which is 2 times 10 to the power minus 6 coulomb, multiplied by the, so now it's not going to be a scalar product of E, of the electric field, which is minus 10I minus 4J, okay, scalar dot the dr is minus 6I plus 12J. So this unit, what's going to be the unit? The unit of the electric field here is Newton per coulomb, and the unit of this is meter. So this will be Newton meter per coulomb. Now, so how do you find the scalar product of two vectors? So if you have A dot B, so the scalar product is AX times BX plus AY times BY plus AZ times BZ. So in this case, we have only X and Y. Okay, so in this case, we have WE, the work done, equals 2 times 10 to the power minus 6 coulomb, then into bracket. So this is AX, this is BX. So multiply the two. So AX times BX, so minus 10 times minus 6, that will be plus 60. Then AY is minus 4 times 12. Okay, minus 12 times 12, that will be minus 48. Okay, minus 48, and the unit is Newton meter per coulomb. So what is 60 minus 48? That is 12. Then 2 times 10 to the power minus 6 multiplied by 12. So you get 2.4 times 10 to the power minus 5 joules. So that is work done. Okay. So you can review your vectors. I think that was from last semester. Okay, from last semester. Yeah. Okay. So next is electric potential energy. So that will be 5.0. Now we have initially defined the work done, and I think yes. So this is question 6. We have initially defined work done as the change in potential energy. Okay, change in potential energy. So it means we can write the change in potential energy, which is the final potential energy minus initial potential energy, to be minus W. Okay, the work done by the electric force. Now, we have also derived an expression for the work done by the electric force, and that expression was this equation 9. Okay, Q integral the scalar product of the electric field and the displacement vector. So we can now write the potential, the difference, the electric potential energy, the difference between the electric potential energy, to be negative of WE. Okay, now, and this will give us the WE. So it's Q. So in that case, we're not going to have minus Q. Okay, minus Q integral Ri vector to Rf, then the scalar product of the electric field and the displacement vector. So this is what we have, and this is the UF. So this is UF minus UI. Okay, so this is also an important equation that will be labeled as equation 11. Equation 11. All right. Now, let me give an assignment on this. So the assignment is that, okay, so this is the assignment. The electric field along the x-axis varies according to the equation. So in this case, this electric field is not constant. Okay, so it varies according to 3x. I, still a vector. So the question is, calculate the change in the electric potential energy of a 4 coulomb charge as it is moved from the point x equals 3 meters to the point x equals 4 meters. So in this case, you are going to use this form. Okay, you are going to use delta U, which is change in the electrical potential energy, as minus Q integral Ri to Rf E dot dr. Okay, because this E is not constant, it depends on X. So in fact, you can change it to I shouldn't solve it. But anyway, you can use minus q integral x1 to x2. So here x is 3xi, then dot dx. Okay, so you can use this to get your answer. So next is potential difference. Potential difference. Okay. Okay, so the potential difference PD. So I'm going to denote it as P dot D. So between 2 points is defined as the change in potential energy per unit charge if you displace a charge from one point to another. Let's say from position Ri to position Rf. So it is the potential energy, the change in potential energy per unit charge. And we have already defined potential energy, the change in potential energy here, which is minus q integral Ri to Rf E dot dr. So in this case, you only need to divide by q, so that you have minus integral E dot dr. So this is what you have here. So this is the definition of the potential difference. So I'll call this equation 12. Equation 12. All right. So let's take an example to illustrate this equation 12. Example. All right. So the question is, the electric field in a certain region varies with the distance x according to the equation E equals 4 over x squared I. So the electric field is a vector, and it is 4 over x squared, the unit vector I. So the question is, calculate the potential difference between a point located at, so Ri is 2 meters, and a point located at 4 meters. So Rf is 4 meters, or in this case, xi and xf, since it's just one dimension. Okay, so let me sorry. Okay, so let me use xi, x subscript I, and x subscript f. Now, the potential difference, delta V, is minus integral, in this case x1 to x2, E dot dx. Now, the x1 in this case is 2, while x2 is what? Is 4. And E is 4 over what? Over x squared. So since this is just in one dimension, so we can remove the vector notation. So the x. So the delta V, and the question also says, yes, very distant x. Okay. Now, so the delta V is now minus the integral of this integral. We can write it as 4x minus 2 dx. And from standard integral, if you have the integral of x raised to power n dx, it is x raised to power n plus 1 divided by n plus 1. Okay, so in this case, it's going to be the integral of 4 is there, then x raised to power minus 2, so we add 1, n here is minus 2, so minus 2 plus 1, minus 1, so that will be x raised to power minus 1 divided by minus 1. Okay, from 2 to 4. So this minus, that will be plus, so that will be 4, then x minus 1, 4, 2. So that the change in potential, the potential difference, is now 4 into bracket 4, 1 over 4 minus 1 over 2. And 1 over 4 minus 1 over 2, that will be minus 1 over 4 multiplied by 4, so that will be minus 1 volts. Okay, so that is the potential difference. So lastly for today, we'll look at the potential due to a point charge. Okay, potential. So lastly, 6.0 potential due to a point charge. Sorry. Well, this can easily be obtained. We have defined many of the parameters that we need. So from our definition of potential difference, we said that the potential difference is minus the Ri up to Rf, the scalar product of the electric field and the displacement vector. Now, this potential difference means V, if we integrate it, okay, it means V of the Rf minus V of Ri. Now, if we take Ri to be infinity, and of course the potential at infinity is 0 because the charge is far away from the field. Okay, so the charge does not feel the field, so the potential at infinity is 0. Then the second potential, the second position, Rf, let's just call it R. Then the potential at that point is V of R. So in that case, we can have V of R, because if you integrate this, so let me write this. So if you integrate theta V from V1, which is V of R1, Ri, up to V of Rf, okay? So in that case, we have V of R minus V of infinity. So this Rf is now R, and this Ri is now what? Infinity. And we said V of infinity, the potential at infinity, of course, is 0. So we can now say this is equal to minus integral Ri is infinity, Rf is what? Is R. This electric field, we can write it as kq over what? Over R squared. Okay, then the R. Now if we so this V of infinity we said is 0. Sorry. So V of R minus 0, so that is V of R equals minus. So if we integrate this, kq over R squared. So it's similar to what we did here. Okay, what we did here. So again, it will be, let me just do it by the side. So it will be kq R raised to power minus 2, the integral. So that will be kq R raised to power minus 1 over minus 1. Okay. So that will be minus kq over R from R to infinity. Okay. Now, this V of R will now be minus times minus, minus times minus is plus. So that will be kq over R, then from R to infinity. Now, if you put R, you have kq over R, then minus. If you put infinity, you have kq over infinity. Any number divided by infinity, which is not 0, then it is 0. So any number divided by infinity is 0. So it means this is just kq over what? Over R. So it means the potential due to a point charge. So if you have a point charge, then it is kq over R. Or you can write it as q over 4 pi epsilon naught R, because k is 1 over 4 pi epsilon naught. So this is your potential, the potential that is due to a point charge. Now, what if you have a collection of point charges, like n of them, maybe 10 or 20 or 3 of them? Now, for a collection of n point charges, you have your V of R to be the summation of the individual contribution. Okay, so that will be 1 over 4 pi epsilon naught, then the summation from I equals 1 to the number, if they are 10 up to 10, qi over ri. So this is what you have. So let me call this is equation 12. So let me call this equation 13 and this equation 14. So this is where we stop for this week's class. So let me give the final assignment, which is the third one. So this is the third assignment. Okay, so this is the assignment. A charge minus Q is placed at one corner of a square of side A, and charges plus Q are placed at each of the other corners. So it means there are three, because there are four corners. One is minus Q, placed at one corner. The remaining three corners have charge plus Q. So the question is, what is the potential at the center of the square? So you have to consider the contribution of the other of the four charges, the contribution of the four charges, okay, at the center of the square. So this assignment should be submitted latest on Thursday. Okay, so see you next time. Bye bye.